Right, so yeah, I'll introduce myself. Yeah, so Nick Quirke, chemistry, Imperial College, and I'm well, we're part of the modelling team in SmartNanoTox, and so I'm just going to describe how we've been using modelling approaches to try and make progress in linking material properties to outcomes, essentially. So we'd like to answer the question, can we measure something at the molecular level which would correlate with the behavior of nanomaterials and cells? And the short answer is that we can do something, but it doesn't reflect the full complexity of a real cell, but we have made progress. So let me start to take you through that. Let's see now, I want to go to next. Try to get off the screen, trying to get to the next one, and none of these controls work. There's not a next. No, okay. So now if I go to, right, I seem to be stuck.
Can you use can you use the arrows, or how you usually change slide?
Usually, yeah, and let me see if I, okay, good. Thank you very much. Yeah, I just click on the right-hand side and it goes automatically. All right, that's good. Yeah, this is a bit different to Microsoft Teams, which is what we've been using. Right. So as Vladimir's already said, this is a pathway-based approach. We'd like an explanation of toxicity based on molecular level interactions between the nanomaterials and the membranes. And we'd like to identify molecular initiating events leading to those adverse outcomes. And then eventually capture this in software that correlates nanomaterials, properties, and toxicity. So in order to make the link between the nanoscale properties of materials, we need to identify key initiating events, and from that we can link to adverse outcomes. Oh, sorry, right, now do that. Good. Right, well, before we can have an adverse outcome, we've got to get the stuff in, and that's endocytosis. And this is the process in which the substances are brought into the cell. The materials being internalized and then surrounded by an area of cell membrane, which then buds off inside the cell to form a vesicle containing the ingested material. Endocytosis can be active or it can be passive. And we are only going to be concerned here with the passive part. However, that's because our key initiating event will be the entry of the material into the cell through the plasma membrane. Now, one can imagine other key initiating events which could include the active endocytosis, but that's not the case for now. Let's just, oh yeah, so once it's in, then the material will be taken up by the autophagic pathway, cell clearance mechanism. Let's take a minute now to reflect on the full complexity of the plasma membrane. At the bottom of the slide, you can see that we have lipids, we have glycoproteins, we have carbohydrates, we have the cytoskeleton, we have transmembrane proteins, we have globular proteins, we have an incredible complexity. We cannot possibly tackle that. Well, we haven't tackled that in the current program because there hasn't been time. One can imagine doing much more, but that's not what we've done. So what we're going to assume is that the lipid is the most important component, certainly the major component, and we are going to concentrate on the properties of nanomaterials interacting with lipids. So once we get the material in, then they enter the endocytic pathway, which means they're taken up by these organelles of various different types, and which mature over time, and the environment inside becomes more and more acidic. So by the time you've got to the autolysosome, you're in a very acidic environment, and one in which you can expect proteins to be broken down and then taken away to be used elsewhere in the cell. So this endoscientific pathway is basically the garbage dump and recycling. Now, if we imagine nanomaterials entering this system, then they're most likely to be covered in a protein corona, which will be removed inside the autolysosome, exposing the bare nanoparticle. So that is perhaps where the damage, if any, would occur, because if the nanoparticle then disrupts the autolysosome membranes, and there are several, then you could get permeation of the acidic interior into the cell, resulting in inflammation, etc. But the key for this study, the key initiating event, is the entry of the nanoparticle into the cell, and not a subsequent effect. Right, so now we've seen it's incredibly complex. It changes with time. How on earth can we build a tractable model of this system? All right, well, for us anyway, the key realization was that there was already an existing body of theory called inelastic theory, which dealt with the wrapping of nanoparticles by infinitesimally thin elastic sheets. And we're going to use that theory as a basis to make progress. You can see on the screen there's a phase diagram which plots reduced tension on the right. On the y-axis, and reduced absorption strength, or free energy of absorption, on the bottom. And so just like a fluid phase diagram, if W or omega there is small or less than 4, then the particles don't adhere. So there'd be no entry into or through the membrane. And then for increasing values of the reduced absorption free energy, then we go through stages of being partially wrapped and fully enveloped. And the fully enveloped state there, we would hypothesize would be the part where the nanoparticle goes through the membrane and is then taken up by the endocytic pathway. So the key initiating is then translated it from experiment into an event inside this elastic theory. It only requires 3 parameters: the surface tension of the membrane, the adsorption free energy for the membrane with the nanomaterial, and the bending tension of the membrane. So we could predict wrapping, which you could interpret either as significant membrane disruption or actually entry into the cell, if we know the adsorption strength, which here is called W, but in the following is going to be KW, and KW represent the adsorption strength on a planar surface, not on a curved surface. And we'll come back to that later. Oh, right, sorry, I keep forgetting. So elastic theory has the potential for fast screening of nanoparticles for toxicity using the inflammation pathway. that is, molecular event is getting in, and then subsequently disruption of the autolysosome and release of inflammatory agents. What are the major challenges? Well, the first one is there's no data for the adsorption strength, except for one material, which is gold. No experimental data and no data from simulation before we started working on this. So without the W or more restrictedly the KW, we can't make progress. Also, of course, there are some pretty big assumptions, including the infinitesimally thin membrane. Now, you know, a real membrane has a thickness of about 4 nanoparticles, nanometers, which is not so different from the nanoparticle radius of many of the systems that we're looking at. So we can't ignore the thickness, really. And it also assumes that W, sigma, and kappa are independent of the curvature, which they're not. So we have some work to do in removing those assumptions while still remaining within the general framework of the elastic theory. So the first thing to do is to try and get information on W, and we're going to do that initially by simulating planar interfaces. So we have a ribbon of lipid membrane, as you see on the screen. We have restraining forces on the two ends that stick out into the solvent, which is water, and we measure the free energy of adsorption of that leaflet of membrane bilayer by essentially measuring the force required to keep it stable on the surface. So details are in the literature, and we tested it against the experimental data for gold, and we got a good consistent result. So we believe this method works. What it does is that it removes the problems caused by periodic boundary conditions. If you don't use the method outlined here, you will never get equilibrium between the water in the bulk and the water that sits between the membrane and the material surface. And so your results will be wrong. This allows the solvent to penetrate all areas of the simulation. And we've done the usual tests on system size. Right, so the table that you see in front of you now is for a range of materials. We're still working on hematite, but what we have here is silica and titania, or in various forms, different faces. And for the moment, let's just consider the pure bilayer, DMPC bilayer, and look at the adsorption strengths. Well, the clear winner here is gold at the top with an adsorption KW of minus 42 millinewtons per meter. Very, very strong adsorption. If we now go to silica, we find that it's an order of magnitude less, and it varies depending upon the form of the silica. It also varies depending upon the percentage ionization of the silica, so acid to base. The strongest adsorption is for amorphous silica at minus 7.5, obviously much weaker than gold, but still significant compared to the other forms. And so that one sticks out, the neutral amorphous silica. If we go to the TiO2, we find generally weak adsorption, although we can see the rutile 101 has and the rutile 100 have a value of around minus 4, as does anatase 110. A very key observation is that the lipid composition of the bilayer doesn't matter too much. If you look at the second line, we've got gold, and it's got gold labeled with an A. So that is gold now on a mixed membrane, 50% POPC, 25% DOPE, 15% BMP, 10% SM. So that is much more complex, but you'll note that the absorption strength is within the error, it's the same. So absorption strength, at least for this system, and we'll generalize it to others, does not depend upon the precise composition of the lipids. What it does depend on, really significantly, is whether or not cholesterol is present. If it is, it halves. So there's a lesson. We've really got to take care of the cholesterol. Anyway, gold's the strongest. Silica amorphous is the strongest from the silicas. It does vary with the ionization. And then for rutile, weaker again. Now, this observation that the disordered silica has a much stronger absorption free energy is consistent with the silica toxicology. Disordered surfaces are associated with inflammation. And for more on that, you can go to this very nice review by Pavan and Fubini. So at least from that table, we see several things, but that observation that the silica, amorphous silica, is the strongest, it is very strong absorption, is consistent with that literature. Okay, now we're going to, we've been talking about atomistic modeling so far. However, if we want to do simulations of nanoparticles being wrapped by membranes, then we really need to coarse grain. And for that, we have used the magic software from Sasha's group to coarse grain S-lipids, which is an atomistic force field from, again, Sasha's group. So we've got a coarse grains now potential. We've taken 118 atomistic sites and reduced them to 10. So now we can run much faster simulations. We need now a force field for that coarse-grained membrane interacting with a nanomaterial. And so what we're doing now is scaling the epsilon in the 1043 potential to reproduce the atomistic potential of mean force for gold absorbing the atomistic S-lipids membrane, and a scaling of 60% roughly gives us the atomistic result, which is the full line. We also need to take account of the fact that the elastic membrane is not infinitesimally thin. We need to modify it, and so we do that by taking account of the fact that the force will act, well, by assuming that the force is acting at the midpoint of the finite membrane, giving you the red line there, and that increases the diameter. Well, one of the things it does is to effectively increase the diameter of the nanoparticle, but also it changes the nature of the complete wrapping. You note the red lines don't meet, the blue do. We set up a coarse grain simulation in a two-dimensional disk, and we put the nanoparticle in contact with that disk, and we can measure then the tension, which is the force in the red lines divided by the radius, divided by 2 pi r. So then we can measure the tension in the membrane as a function of the penetration depth of the nanoparticle. If we just use the unmodified elastic theory, we get the dashed lines for the different sizes. If we use the modified elastic theory, then we get the we get the full lines, 15 for 10 and for 6, and then the simulation results, coarse-grained, are the dots. And we get that agreement by in 2 ways. One, by obviously changing the radius of the particles, but also by allowing by allowing the absorption free energy to vary with the size of the nanoparticle. And that then allows us to predict minimum diameters for complete membrane penetration for different materials. So the equations there, 15 and 16, you see, this is the W for the supported lipid bilayer as a function of the radius A of the material, of the nanoparticle. So the planar surface value is minus kW, and then we have a variation with the with diameter, plus we have the change due to the bending tension. And with that now, in the table, we have the critical diameters below which you will not get penetration of a liposome made up of the lipids that we've been using in our model membrane. Gold always wraps. The kW is so strong that all the gold nanoparticles would wrap. But then as you go to silica, for example, we find that quartz won't wrap until the diameter is around 40, but the amorphous silica does at 7.5. So if you have a mixture of amorphous and quartz nanoparticles, your membrane will, the amorphous nanoparticles will be wrapped at for diameters over 7.5, whereas the others won't. So you can already see you'll get a separation of different materials. We've also done simulations for the spheres and cylinders by taking the various faces that you would find, and again you can see there's a big difference actually between rutile nanotase, and also you'll see that the cylinders wrap far more easily than the spheres. Okay, now this is not the only consideration, because we're now really talking about liposomes in a solution of particles. And what we can do is to use these data to determine a maximum particle concentration for complete wrapping to occur, because as particles enter the liposome, they take with them lipids, which increases the tension in the membrane. Of course, this will not perhaps be the case for real cells because they have lipid reservoirs, and so you wouldn't get a tension change. So what I'm about to say now really only applies to systems without a lipid reservoir.
Nick, you're over time already.
All right, okay, so I'll just leave that and go on to say that we can make predictions for real systems using all the theory that I've mentioned in the previous slides. We can say, well, what would happen to gold on a liposome surface? The liposome is around 200 nanometers. And we find that that for small gold nanoparticles, 5 nanometers, we expect complete wrapping, but for 25 nanometers, we don't expect it. And we also would predict that the nanoparticles are likely to form up into cylindrical shapes because that produces a much smaller critical diameter. If we compare those predictions to experiment, that's exactly what is seen. These are Claudia's experiments are gold on liposomes, and our predictions are borne out. The small ones clump together to make cylinders. The medium and large, only partial wrap. So what have we got? New physical property data for empirical correlations, new coarse-grained simulation models, first steps in extending elastic theory to nanoscale systems, first description of concentration effects and size effects on nanoparticle wrapping. This will all be available in a code which you can use to try and understand the behavior of nanoparticles when they encounter either liposomes, GUVs, or cells in terms of minimum sizes for wrapping, and also the effect of geometry on that wrapping behavior.